Okay, everybody, welcome back. Thanks for checking in. First of all, I gotta make a disclaimer. I'm recording this out in the hallway, so you may hear people walking by or teachers in rooms nearby. So I apologize for that if that becomes distracting. I also still have a cold as well, and I'm kind of hoarse, so all those things together, I hope you bear with me. So this is going to be the section on Hooke's law, but I first want to start out with an example, example 611, which actually just deals with tension. So this is going to be example, and then Hooke's law, and then another example. All right, so I'm just going to put it all together right there. Just follow along with me, okay? So, so this is still a problem dealing with tension. Tension in a string or a rope or whatever you want to call it right here. And the question is, you've got this mechanic who was pulling or applying a force on this. Yep, I shouldn't make that blue. I'll make it a different color so it stands out. Make it red. He's applying a force on this string to lift up this heavy engine. All right. So he's applying a downward force, and what do we call that exists in the string as a result of that? Well, we call that tension, right? So he's applying that in that string or that rope, and the tension is existing evenly all through this rope right here, okay? So he's applying the tension. He's supplying the force to hopefully move this engine block up. But to find out how much he needs to apply, we need to look and see, well, what does he want the engine block to do? All right. Oops, I didn't mean to circle that. I meant to just draw a dot around it. He wants the engine block to move upwards at an acceleration of 0.5 meters per second squared. So let's go ahead and write that in. That's the acceleration of the system. Okay? System being the engine block right here. Okay? I should say acceleration of the system. And that's 0.5 meters per second squared. All right? Positive, upwards, right? So it's going upwards. All right. What's the mass of the system? The mass of the system, in this case, and the only thing in the system being the engine block, is 100 kilograms. Okay? 100 kilograms. And so we can write a statement for the net force on the system. Net force of the system being mass of the system times the acceleration of the system. Okay, that's great. That's wonderful. But what we really want to find out is what's the value of one of these forces acting on this this engine block right here. All right. Well, let's look then just at the engine block itself. All right, just this right here, and I'm going to draw on this diagram instead of making a separate one. There's a series of component forces acting on the engine block. First of all, since the engine block has mass, and since it is on Earth, it's always going to have the downward force of its weight force. All right, mass times gravity is its weight force. So that's pulling it down. And if there was no pulley system on this, the engine would shoot down to the floor because, as things tend to do, they are accelerated downwards because of gravity. But there are other forces acting upwards, and I'm going to change this tension force color to make it green right here. All right, acting in the opposite direction. There's a tension force acting in the string upwards, and by the way, since the string is looped over a pulley that is attached to the engine block, it is applied twice. That tension and this tension right here are both supplying an upward force to support this engine block. All right, now all these T's are the same thing, even though this is red right here. All right, but if we look just at the engine block, we can say, all right, there's three forces acting on it. The net force, let's see, I'll write this in blue. All right, the net force in terms of all the component forces acting on that one part that you care about, the engine block, can be described as, well, the upwards force of T, all right, plus another upwards force of T, tension, existing in the string, minus the downward force of gravity, right? Gravity being mg, right here. So, look at our whole system, right? The whole system is accelerating at a certain rate and has a certain mass. We're assuming that the rope doesn't have any mass right here. Okay, but if we look at the one component that we care about, we look at all the forces that are acting on it. Downwards gravity, upwards tension, and another upwards tension right there that is being supplied through the rope. Now all we got to do is solve for what we don't know. What are we trying to find out? We're trying to find out what that tension is right here, or really how hard must he pull. So let's just go ahead and write this out. I'm going to scrap the color coding right now and just go with black. But since this is equal to that, we can say mass of the system times acceleration of the system equals T plus T minus mg. All right? Or we could say 2T times mg. So we'll bring our mg over. So mg plus mass of the system times acceleration of the system equals 2T. Right? And so the tension, that is how hard the mechanic must pull, is going to be mg, you guys hearing yelling in the background, plus mass of the system times acceleration of the system, all right, over 2. That's going to be our working equation right there. So all you need to do is plug and chug and find out what T is. For the sake of time, I'm not going to do that. I think you guys can do that. We know the mass of the system. We know the acceleration of the system. We know what gravity is right here. Divide that all by 2. You'll be able to solve for what the tension is that he needs to apply. By the way, he's using mechanical advantage right here. He's using a series of pulleys to make it easier for him to lift it up. He's basically taking his force that he's pulling and he's multiplying it by 2 so that it'll make raising the engine block a little bit easier. So we'll talk about that probably a little bit later, though. But you can solve for T, I believe, and for the sake of time, we're going to move on to Hooke's law, which deals with springs. So Hooke's law, and this is what I believe problem 2 and problem 4 in homework 6.6 is on, deals with springs. And you know that a spring, or hopefully you do, is an object that gives you a feedback force, right? So here's a spring right there, all right, kind of at an angle, or you might indicate a spring kind of like that. That's fine too. But a spring doesn't apply a force unless you do what to it? Unless you squish it down, right? Unless you displace it somehow. So at its equilibrium length, it's just sitting there, minding its own business, not applying a force. But what Hooke's law says is that as you stretch or compress it, that is, as you displace it some amount, oh, that's a bad color, it's just black. Go with something more, go with like red. As you displace it some amount, it is going to feed back with a certain force. All right, now you might be asking, well, what the heck is this K right here? What is this K? What K is a constant of the spring. It's kind of it's a value of the spring. You know that not all springs are the same. Some springs, like you pull out of a clicky pen, are really easy to squish. Other springs, like that hold your car up, are very difficult to squish because they have different thicknesses and different values. If we were to turn this equation around right here, all right, and solve for K, all right, it means we have to divide by our X, right? So that would be the force of the spring divided by X right there. So what is force measured in? Well, it's measured in newtons, right? And displacement is measured in meters. And so the units for this K value are newtons per meter. We say if a spring has a K value of 3 newtons per meter, all right, or 3 newtons per meter, like that. If you displace it, and that's a pretty weak spring actually. If you displace it by 1 meter, it will feed back with a force of 3 newtons. Whether you squish it down or if you stretch it, it doesn't really matter. There's 3 newtons for every meter. If you displace it 2 meters, it'll feed back with a force of 6 newtons, and etc. So that's what that K value is right here. This is the spring force. This is how much you displace it, and the K value is this newtons per meter, or some value of the spring. And in most cases, you're going to be provided with that. I guess sometimes you might need to solve for it, but it is some property of the spring itself. And that's it. It can't be calculated any other way. It's just some property of the spring. We call that the spring constant. Like I said before, it measures the stiffness of the spring. All right, if a spring is 10 newtons per meter, it's a stiffer spring than if it is 1 newtons per meter. All right, so this might be a really thick spring like that, and this might be a really skinny spring right here that you would pull out of a pencil or something like that. Now, depending on whether you push a spring in, all right, whether you compress it like that, or whether you stretch it end to end, that might give you a positive or negative force. We don't really care about whether you're compressing it or stretching it. All we care about mostly is just the magnitude of that force. I'm assuming, well, we're going to assume that we know what direction the spring is pulling or pushing when we get to it. So all we really care about finding is what that spring force is right there. And the force that a spring is applying is nothing more than its spring constant K times the displacement that you stretch it, and that's it. So we're going to see if we can apply that in a problem, and hopefully that'll help you with some homework problems as well. Okay? So here we have, I guess, a toy bulldozer, something like that. All right, and it is attached by a spring to the wall. And so as you turn this thing on, I guess it's motorized, it's going to be moving this way. It's going to be moving towards the right. Okay, so let's write some things down that we know about this spring right here. I'm going to just write it right on here instead of a separate slide. Do this in red. Okay, the spring constant, that is K. Right there is 1,300 newtons per meter. I told you those other values for other springs were pretty weak that I mentioned before. But 1,300 newtons per meter. All right, so as you stretch it 1 meter, it's going to pull 1,300 newtons back. If you stretch it less, it'll pull less. All right, and it's stretched. You might say your x or your delta x is 0.45 meters. Okay, you want to find how much force, find the magnitude and direction of the force that the spring exerts on both the wall and the bulldozer. All right, so let's find out what that force is. All right, let's find out the magnitude first of all. The spring force, the magnitude. Hooke's law says that it's K times X. So that's 1,300 newtons per meter times how many meters? 0.45 meters. All right, meters cancels out. We're going to have a value left in newtons, and that's going to be 585 newtons. All right, let's dotted line box that right there. That's our magnitude. All right, now at equilibrium, right here, the spring is not stretched, just minding its own business. But as you pull it, as you stretch it out, okay, that's the displacement that you're applying. All right. Well, what do springs do? They tend to resist the direction of pull, so that as you might say this is your delta x in that direction right here. As you displace it, it is going to pull back in the opposite direction. So the spring is pulling back on the bulldozer, so that would be force on the spring on the bulldozer. And it's also going to, if it's still attached to the wall over here, it's going to pull back on the wall. So we can say that's a force of the spring on the wall. So we could say for part A, that is the wall being A, and the bulldozer part B right here. A, we can say the force that the spring exerts on the wall is going to be, let's call this, that direction going to be positive, that's going to be negative, right? We can just say that it's 585 newtons, okay? Part B right there, the force that the spring exerts on the bulldozer is going to be negative 585 newtons. All right, if we apply the coordinate system right here. So that was actually pretty easy. Like I said before, Hooke's law is nothing more than a means by which to find a force, pardon me, as a result of some string being stretched. Being stretched. So you've got the spring constant, and you have some displacement that it is being stretched. You can solve for whatever unknown you don't have. And that's it. In the future, I may give you, you may come across a problem where you're given the force that is applied, or that the spring creates, and you might be given, 3 newtons, and you might be given the x, that is, it is being stretched 0.5 meters. That's pretty terrible right there, 0.5 meters. And so you might have to find out what K is, but you can do that because we know Hooke's law is the force of a spring equals K times X, and you can easily find that K right there. So that's it. It's just this relationship that I want you to understand. The force in a spring is the spring constant, K, times however much is being displaced, whether it's being pushed or whether it's being pulled. All right, so that's example 611 on Hooke's law. And if you have any questions about it, make sure you come see me or ask me about it some other way. Thanks for watching. In the meantime, I'll look forward to seeing you on the next one.